Okay, so we've passed where we need to be for the first semester test. So we will probably wind up doing quite a bit of revision in the run-up to the first semester test, so that you can do as well as possible. We'll still keep some new work coming in because the second semester has a lot of content that needs to be covered. Try and do as well as possible in the first semester test as well. Past papers for the first semester test are available on Eve under lectures from 2007. Not under lectures, under notices. There's a link there, 2007 to 2020, so you can start going through them. Last year's test had multiple possible questions for each. There were a bunch of variants, so that's a whole bunch of separate documents that were auto-generated for each person. But the rest look quite familiar, and you can still go through all the variants, and we'll go through them as well as part of the revision. And then at the moment, it's a very good question. Will semester test 1 be written on campus? At the moment, the understanding is purely online, but those things, as you know, can change very quickly. So at the moment, semester test 1, at least, the understanding is online, and obviously semester test 2 is too far in the future to know anything about it. But semester 1 online at the moment. Please keep checking Eve. The situation can always change very quickly. So that's a good question. So if you look under notices, the question was, where can we find the past papers? If you look under notices, you'll see there is a notice for this first semester test, and that notice will be updated if there's any changes. I'll also update it again just to say what the scope is, but the scope will be the same as the past papers for the past couple of years. So basically up to basic inheritance without polymorphism. So the stuff we're going to move on to today is out of the scope, but the main emphasis on pseudo objects, basic C++ object orientation, and composition and delegation, the key components for the first semester test. Yeah, under notice board. The file was too big to upload as a lecture, so it went under the notice board. All right, and then let's carry on. I'm not 100% sure exactly. He said slide 18, but let's just quickly do a quick recap of where we are for inheritance. And I think he said slide 18. So inheritance is a relationship as opposed to composition and aggregation, which are has-a relationships. So basically the idea for is-a relationships is that you create these functions and data types that expect the higher level classes, the more general classes, and they can then work on those higher level classes even if you've got 1,000 different variants of them. So for example, every employee is a person, but maybe you have a thing to track vaccination status of people, even though it's an HR system. So you don't want to write separate functions to track employees and part-time employees and full-time employees and fixed-term contract workers and all of the other possible kinds of employees you could have, because they're all just people. So you'd rather have a function that tracks the vaccination status for people, but you want it to also work on those other types. So you need to create a link between those types so that an employee is a person, and a fixed-term contract worker is an employee, which is a person, and a permanent staff member is a full-time employee, which is a person. So that you can create these different functions that work at different levels of abstraction for all of them. So that's the idea, and also it allows you to try not to repeat yourself too much, because by creating something to be an instance of another, a specialized case of another type, you don't have to repeat all of the data that's the same and all of the behavior that's the same. So all functions that a person, or member functions that a person has, an employee automatically has as well, because they are a person. Likewise, all the data that you might store for a person, their age and the dress and whatever else, an employee will also have those, but extra stuff as well, like an employee number and a line manager and whatever other things you might keep track of for an employee. So there's less code sometimes for the more derived classes, but they actually have more information because they have all the information from the previous base classes, but you only specify the difference between those two classes. So in C++ terminology, the term is a base class. In other programming environments, they sometimes call it a parent class or a super class. And the ones you create from it, the specialized versions, we call, in C++ terminology, derived classes, and in other terms from other programming languages and general terms, child classes or subclasses. So the important thing is that they inherit the properties of the base class. C++, as we said, has different kinds of inheritance, which is very unusual. We're only going to use one, really, which is single public inheritance. So C++ allows for different visibility level changes when you inherit. You can downgrade things from public to private or public to protected or protected to private. If you use public inheritance, you keep everything the same. Nothing changes. Doesn't mean everything becomes public. It just means that which was private stays private, that which was protected stays protected, that which was private stays private, that which was public stays public. So everything just stays the same. And then having more than one parent class is possible in C++, but it's very easy to do wrong. So we will try not to do it wrong. So mostly we will use single inheritance, which most programming languages only allow you to use. I'll explain to you what the problem, well, you probably were explained what the problem was, but it is avoidable, but you can implement any architecture using a single inheritance model, which is why most programming languages only allow, for example, Java and Visual Basic, .NET, and C#, and many common programming languages only allow single inheritance. That means one parent. So here's an example of something with one parent, similar to what we did in class today, except we didn't bother to further constrain it to a square in the tutorial. But you have a base shape class and then a derived circle and rectangle. Shapes will have things that are common to all shapes. In our case, we had the position of it, its location, and its color. But circles have extra information like a radius, and rectangles might have length and breadth, and a square might constrain length and breadth to always be the same value. So you can create these inheritance hierarchies. The syntax to create a derived class is to have a colon after the class name, a member access specifier, so either public, private, or protected. For you guys, always public, and then the base class name, the parent class name, the super class name. And then you just define the differences between the two. The one, i.e. the new things that the derived class has that the base class didn't have. The one thing you do sort of kind of repeat yourself a bit with is the constructors, because they don't make any assumptions that you automatically inherit constructors from your base class, because you might create derived classes in very different ways to what you would do with the base class. So if you do have things that are similar, you can pass them back up to your base class constructors using what's known as constructor chaining, which is basically the same thing as constructor delegation, except not within the class. It goes up to the parent class. You will still have the public members, and you can downgrade their visibility. We won't. You will also include the data or member functions that you can add, and then you can change the behavior of existing member functions by creating in a derived class a member function with exactly the same name, not a difference in terms of a name and parameter list. So it's not overloading where the parameter list differs, but it's what we call redefining or overriding, depending on a key difference we'll point out now. And basically, you're then changing the behavior in the derived class so it's not the same as in the base class. Consider how an employee spend their day. Let's say you have a member function called spend day. An employee will spend their day very differently from a child, who will spend their day very differently from someone who's on holiday or someone who's seeking work. And you can basically realize that by redefining the spend day function differently for each one. Different kinds of employees will also spend their day very differently. If you're a nuclear waste disposal technician, your day is very different from someone who is an accountant, right? So you can redefine those behaviors to be what you need them to be in the derived classes. So yeah, so basically it's exactly the same. You just basically implement it as if it were a function that just happens to have exactly the same name and parameter, numbers and types and order. So the signature of the functions is exactly the same. So yeah, so you can, if you want to, in the derived redefined version, still call the base classes version if you want to use it inside your redefined version. You just simply need to specify the full name of the functions. That will be base class : and then the function's name, and then you obviously call the thing. So here we have a rectangle, which has got a length and a width, as well as axes and normal functions for it. And you could change, for example, the behavior of calculating the perimeter or calculating the area to use the correct formulas for a rectangle, which is exactly what you might want to do. Or you could extend a rectangle into being a box, which is a rectangle with height, and all you need to specify is the height member, as well as the axes and mutators related to that, and anything else you might want to change. For example, added volume, and you might change some of the other behaviors as well, or introduce new ones. In the derived classes, you don't have access directly to the private members of the base class. So in your constructors for the derived classes, you can either send the work back up to the base class using constructor chaining, or you can, of course, use protected data members to have that visibility between yourself and your derived classes. So that's the basic idea. The destructors as well will all need to be executed for a particular class. So basically the order is that the constructors all execute first in order from most general to most specific. So let's say you had a person that was an employee, that was a person, that was a let's say a contract worker, that was an employee, that was a person. The order of the constructors will be person, and then employee, and then contract worker. That'll execute in that order, because you basically build the house from the ground up. You need that foundation of the person data needs to be initialized before it can make sense to convert that into an employee, which needs to be completed before that makes sense to convert that into a contract worker. And likewise, the destructors will run in reverse order from most specific to most general. So in that case, if we were to have a contract worker go out of scope or be deleted if it was freezed or allocated, the destructors would run contract worker first, then employee, then person. So basically you can think that you disassemble the house from the roof down, but you build it from the foundation up. So that's important to note. As we've seen, every class will have its own header file and CPP file, including the derived classes, and we'll hash include the ones we want to inherit from. And as you've seen, sometimes you can wind up with cycles, not in terms of the inheritance hierarchy, that has to be cycle free, but if you have functions that use the base classes, and the base class needs to also be aware of another type that uses it as well, you can get those cycles of dependencies that kick in, just like with composition and aggregation and delegation. And to fix that, you use forward declarations like we did in today's tutorial, and or sometimes you can break the cycle by moving the required let's say the structure in that case, which was required by both of them, you can move it to its own header file, and then it doesn't cause a problem. So watch the tutorial if you would like an example of that. We've seen, of course, the inclusion of multiple headers can be prevented with hash include, with if and def preprocessor guards, but that doesn't protect you from the cyclic dependencies that might kick in. Here's an example of inheritance in real life. You've seen that input streams and output streams are both kinds of IOSs. And well, I'll skip these for now, but let's say, for example, CIN is a kind of input stream, which is a kind of input-output stream, and COUT is a kind of output stream, which is a kind of IOS. IF stream and OF stream we will look at this semester. It's the file stream, so we'll be working on them definitely before your second semester test, so you will have them in your practical test, but you won't need to know about them for the first semester test, so don't worry about it. But it's basically file handling streams. Now you can get, as we'll see later on when we do the file handling, an F stream which is both an input stream and an output stream. So you can have inheritance, multiple inheritance. So you can have streams that are both input and output streams. You've seen it before with a string stream, for example, is an easy example. You could stream into it and stream out of it. So it's both an I stream and an O stream. That's an example of safe multiple inheritance. Let me just quickly explain to you when multiple inheritance isn't safe. So let me just see if there's any questions. Why must you always use public inheritance? Good question, because it doesn't change anything. So it's very weird that C++ lets you downgrade visibility from public to private, or public to protected, or protected to private when you inherit from something. Most programming languages don't do that at all. So all of the sort of discipline of object-oriented programming sort of builds around not changing that. So we will just program in a style that's like other programming languages. If you have a real good reason to downgrade them, you can, of course, do private inheritance or protected inheritance, but you won't. Almost all programming languages don't work that way. All right, so an example of when multiple inheritance is a bad idea. I'll give them verbally. There's two ways in which it can happen. One is where it's just a bad idea, where people get lazy and they think that inheritance is a way to reuse functionality without having to write the code again. There are ways to do that, but inheritance's main job isn't that. Its main job is specialization and abstraction. So basically creating more general types that you can work with and more specific types that do the right thing. If you're just using it as a way to reuse functionality, you're going to have a bad time. So if you think about, let's say you're making a hierarchy of classes to represent animals. This is a very common example that's done in object-oriented programming, where you'll have, let's say, mammals, and you'll have a cat as a kind of mammal, and a lion is a kind of cat, and a tiger is a kind of cat, and a dog is a kind of mammal, and a wolf is a kind of, or canid, or whatever you want to call it, a wolf is a kind of canid, and a dog is a kind of canid. Those are all possible. But let's say you're super lazy and you're in charge of writing the classes for the Australian animals, and you come across the duck-billed platypus. Now, duck-billed platypus is a very weird animal. It has a beak like a duck. It's got webbed feet like a duck, but it's got fur like a mammal. It also makes milk like a mammal, but it lays eggs like a bird, but it also has venom like other poisonous animals, or at least the males do in their spurs. It can also sense electric fields like a shark can. So duck-billed platypus is a very weird animal. So if you're super lazy, you can try and create a duck-billed platypus by making it is a shark, so that I get the electrosense. It is a duck or a bird, so I get the egg laying. It is a mammal, so I get the fur and the milk production. But that's nonsense. It isn't a shark. It isn't a bird. It's a monotreme. It's technically a kind of mammal, but using multiple inheritance that way to just reuse code is a very lazy and dangerous technique, because it means that someone might write a function that works on all sharks, and all of a sudden you can send a duck-billed platypus into that function with no errors, even though a shark. So you must never use the is a relationship just to reuse code. So that's one example of where multiple inheritance is dangerous. Another example is what we call the diamond problem. Subclass is the same thing as derived class. It's another language. Other languages use that term. So derived class or child class or subclass mean the same thing. Base class or parent class or superclass mean the same thing. They're just different words, different languages used for the same concept. The C++ terms are base class, So that would be like person, and derived class, that would be like employee. So that was the one example, trying to create like a hybrid double platypus class by using inheritance where you shouldn't is a bad idea. Another one is what we call the diamond problem. And that's where if I've got a base class, I'll just show you something here. It's not going to open a class, it doesn't make any sense. Note that. If I make a base class, and let's just call it class A. And class A defines a function. And let's say they're CPP files and it fully defines them, or they're lazy and we implement them fully here. Right, so they have complete definitions. They're not just interfaces that say that we will support operation M, we don't know what it is. It's got a full defined meaning. So we've got another class called B, also defines a function called M. And then let's say we've got a class called C. Let's give them better names. Let's call it parent A, parent B, to follow, and then we will have the child class. Sorry, parent A, parent B. Okay, parent A, parent B, they each define name. Yeah, I could do it like this. This is fine, but there's actually a better way of doing it. So let's say we have a base class. So let's call it grandparent. Story. Right, it has the function M as well. We say that parent A inherits from grandparent, and parent B also inherits grandparent. And then we will have a grandchild class that will inherit from both parent A and B, or we call it child or whatever, it doesn't matter. So this is called child, and it inherits from both parent A and parent B. It doesn't define anything. It doesn't define M at all. It doesn't redefine it. Whose M applies here? Is it parent A's M or parent B's M? There's a diamond that's formed where the grandparent defined that this function must exist. The two derived classes from that base class provided different implementations for M, and then the child inherited from both of those middle tier parents and didn't provide their own implementation. Whose version of M applies here? It's undefined, right? So that they call the diamond problem. This is just the simplest version of it, but you can get diamond problems that are quite long, with very long cycles in the inheritance graph, which cause these sort of problems. So as you can see, incest is bad. It causes all sorts of weird problems in the children. And C++ says just be careful. Don't do it in a way that doesn't cause problems. So you're the programmer, you know what you're doing. Most programming languages are, people are stupid and programming is hard, so let's not let them do it at all and avoid this entire class of problem. So I'm just pointing out to you that it does exist. Multiple inheritance does exist, but it does have a certain catch with it that can cause problems too, really. People can be lazy and just use it to reuse code, and B, you can get these conflicting definitions of it. So that's why. There is a safe way to do kind of multiple inheritance that never cause this problem, which we will discuss under polymorphism, because you often do want to have something be compatible with multiple types, but not in a way that can cause this diamond problem to exist. So we will discuss that approach going forward. It's also not in the first semester test, so don't worry about that, but it will be something you'll use in the second semester test and in your practicals. So that's that basic idea. Okay, I think we're all good. Let's carry on. So there we go, inheritance hierarchy. So yeah, so one way to do these things is, you define the functionality that's related to what you are. And if you define only that functionality and there's no clashes, so actually the input stream and output stream hierarchies are a very good example of safe multiple inheritance, because the I stream only defines stuff related to input, the O stream defines stuff only related to output. So if you inherit from both the input stream and the output stream class, like for example the string stream does, there's no conflict, because you only get input related stuff from the one parent and only output related stuff from the other parent. There's no overlap, so there's no problem. We call that style of programming mix-in classes. Other programming languages have finally, after decades, started to implement traits, but C++ has had them forever. But for you guys, our style will avoid multiple inheritance altogether. I'm just telling you it exists, because in fact some of the classes you work with use it, like string stream, but we won't do it in our solutions. There is a safer, although slightly longer way of doing it that avoids the problem altogether. That is more like how other languages work. And we've seen protected sits in between public and private. So what protected means is that it's safe for you and your children. You, the base class, and your derived classes and their derived classes. They can access the data directly. Your parent class can't access, the things that aren't in your inheritance hierarchy can't access them. So you've seen the inheritance approach. You specify the class name before, colon, member access specifier, and then base class, and then public, private, or protected. We will always use public. It just doesn't downgrade the things. So don't worry about that. And then object-oriented design and object-oriented programming. So we've seen encapsulation before. We saw that last when we did week 1. Week 2, where we did the normal C++ classes. The key things to learn about there are private and public, access of functions, and mutator functions, and constructors and destructors. They're all there to wrap data and behavior that are related to a single entity together into one unit. We've now seen inheritance that lets us reuse existing classes by way of an is-a relationship. We've also seen, although that's not listed here, the ability to reuse classes through way of has-a relationships, of which we've seen 2. We've seen aggregation and composition, the strong and the weak and the strong version of it. And then polymorphism is what we're going to move into now, which is the ability to have that dynamic behavior. For example, each person spends their day differently. If you've got a car that you need to lock, and a house that you need to lock, and a safe that you need to lock, and a phone that you need to lock, they're all lockable, but the way in which you lock them is very different. So, but that ability to say, lock yourself, whatever you are, and have it lock itself in the correct way is very powerful. And we call that sort of expression polymorphic, because it's the same expression, thing, lock, but it behaves according to the type of thing, not according to the name of the function only. So we will be looking at that in more detail now. And we've seen an object-oriented design. The object is the fundamental entity. Debugging is done at the class level. So if you the classes are the source code you write. They define the types. The instances of those types are the objects. So your work is going to be done at the class level rather than at the object level. But when your program's running, it's going to be a bunch of objects that will be sending messages to each other, calling each other's member functions to solve your problem. Object-oriented design encourages code reuse, whereas object-oriented programming is a way to implement an object-oriented design, but technically not the only way, although it's much more natural to use object-oriented programming to implement object-oriented design. We've seen that C++ supports object-oriented programming through the use of classes, and we've seen why it's better than the kinds of structures that only existed in C for doing it. We've seen that you can overload function names. We saw that with the constructors are all overloaded, same name, different parameter list. And we'll see now that you can also, well, we've heard that you can redefine behaviors in an inheritance hierarchy. And we'll see that if you do it properly, you can do what we call overriding the behavior, which basically means it'll work polymorphically. We'll see later that there are many kinds of polymorphism that exist in this. Inheritance-based polymorphism is just one kind of them, and another very common kind is called templates, which you've used in the sense that vectors are a templated type, basically container of type T. We'll create our own, and we'll see now coming up that C++ provides a special kind of function if you're trying to do that inheritance-based polymorphism called a virtual function, which basically lets the decision about which version of the function to run be put off until runtime when the types are all known, rather than at compile time where there could be some uncertainty. So the objects are created. You've seen that. So when you create a stack allocated variable of a class type, that will instantiate an object. Likewise, we've also seen if you create a pointer to that type and use new, the object will also be instantiated. Likewise, if you delete it, it will be destroyed. And then objects speak to each other via function calls, which is the equivalent of them sending messages to each other. We've seen that objects have an internal state and an external state. The state refers to all of the member variables and their values. So for us, we keep it that the external state is only constants. It can't change. But the internal state can be changed, but only according to the rules of the type via the mutator functions and the constructor, so that they can only be changed in the way that the rules of the logical rules of your type will allow. We've seen that private members form the internal state. We've seen that public members form the external state. We've now learned that protected members are between public and private in an inheritance hierarchy. And technically speaking, only the object should manipulate its internal state. You shouldn't ever return a pointer to your internal state or a reference to your internal state, because then someone can skip the rules of your type and do illegal changes to your state. We've seen that for analyzing problems, we identified the nouns and the verbs. Now, important nouns will become the classes. Important verbs will become the member functions. And lesser nouns and adjectives and so on will become the member variables, the attributes of the class. Okay, so if we wanted to, we did this in the tutorial there, so I'm not going to spend too much effort. We didn't do a cylinder, but basically, if you identify the different shapes that you want to work with, you can then create a hierarchy of the shape types, but you also identify what abilities you want the shapes to have. In our case, we wanted them to be drawable, but you could also calculate area and perimeter and all sorts of other things with them if you wanted. And then what information do you need at each level? So for example, for us, we put shapes would have a location and a color. In this case here, cylinders will need things like a dimension and the ability to give you surface area and volume. And then you basically need to decide what information must the object store, what information must the what behaviors must it provide, and decide on how visible each of those must be. I think we can live with that. I think that basically just recaps what we've gone over now. Let's go quickly. Composition and aggregation has a relationships. Inheritance is a relationship. Single inheritance is where each derived class only has one base class, i.e. each child only has one parent. Multiple inheritance, each derived class can have more than one base class. Can be safe, can be dangerous. We won't do it. We've seen public, private, and later on protected. If you change the behavior of a member function in a derived class, that's redefining it. And we'll see if you add this virtual function ability to it, it's called overriding and makes it more polymorphic, more flexible. We've seen that you can internally, well, before, the previous weeks, we saw that you could send work between the different constructors using constructor delegation, but you can even send work up to your parent class, to your base class, through constructor chaining, it's often called. So that you don't have to repeat the work that you did in the base classes constructor again in the derived classes constructor. And then, yeah, if you've got composition or aggregation, it means that one of your member variables is going to be an object of another class type. And if you send behavior to it to do work on behalf of the container, then you've got delegation. And then some basic principles of object orientation, say the three most common ones, but certainly actually not the only three. There's a bunch of different ways of stating what principles object-oriented design have. There's a very famous one called SOLID. These ones will do as well. SOLID is a bit more in-depth, so we'll stick to this for now to get the basic principles out of the way. But and we've seen the steps for summarizing and solving the problem. So what you need to know for the semester test is up to what we call it, inheritance without any polymorphism. So the stuff we were going to start on next, polymorphism, is not in the scope of the first semester test. And the first semester test really focuses mainly on pseudo objects, and it's the only time you'll have to do pseudo objects again before you can throw them away forever, unless you decide to program in, let's say, the Linux kernel or something else that uses that style. So pseudo objects, followed by normal class stuff, so constructors, destructors, accessors, mutators. Then has and is a relationship, has a relationships mainly, so composition and aggregation. So remember to create the thing in the constructor, delete it in the destructor, and delegate to it in the function that has the same or very similar name between the two. And then is the relationships in the form of inheritance without polymorphism, where you just basically need to know about protected and the fact that you can reuse the existing behaviors from a base class in a derived class. So I think it's a good place to stop now. I'm not going to start with the next set of slides now, but we have reached where we are for the semester test. And later, tennis code. I did it in the tutorial, and then I didn't even do it here. I don't even remember what I said it was going to be in the tutorial, so I'm going to make up a new one. But thank you for reminding me. I don't know. There. It's not the same code as I said in the tutorial. The tutorial shouldn't have code, but this is the one I remember now. So this is now the code. Thank you for reminding me. And I was just going to design. Ood is a virtual. Okay, we'll discuss that when we do polymorphism. So I'm not going to worry about it now. But yes, this we'll discuss the rules for polymorphism going forward. If we have multiple constructors in our base class, would we call the base class? Yes, we will. We did that in the tutorial. So take a look. Ligers, yeah, the hybrids. I should. No, funny. Anyway, are we going to get past papers? You've already got them. They're available under notices, and we will go through them in the tutorials and class leading up towards the semester test. No, you can look. You don't need it. You've already logged in here. You don't need it at all. You don't need the code. You're done. Okay, I have to leave now. So thank you very much. And see you later. Okay, bye-bye.